The appearance of life on Earth is known as abiogenesis. This is the seemingly sudden emergence of something out of nothing, of living things out of non-living matter. It's the arrival of the most basic cellular organisms at the very beginning of the chain of life on our planet. Up to a point, it's wholly accepted too, with most timelines eventually winding all the way back to the very first cells sprouting in or close to hydrothermal vents more than 4 billion years ago. These vents are cracks and punctures in the deep sea floor, ejecting out water that's heated from the Earth within. And scientists believe that it's here where the first breeding grounds for life may have been established. However, as compelling as all of that is, there is still a certain degree of the unknown if we head even further back. The vents are often put forward as prime locations for early evolution because they will have provided what are more commonly referred to as the building blocks for life. But what does that actually mean? To some degree, you might call the basic elements that make us the building blocks of us, such as hydrogen, carbon, nitrogen, and oxygen. More typically, however, we're referring to a more complex stage, and to proteins, which are the key ingredients inside our bodies for a range of crucial tasks, all of which might reasonably fall under the umbrella term of biological upkeep. Proteins are what maintain our cellular structure. They can issue repairs when things go wrong. They drive vital bodily functions, like muscle contraction and digestion. Some proteins double up as messengers or hormones to further regulate our bodies. Others are charged with fighting infection to ensure you stay healthy. Ultimately, life is teeming with these incredible, complex molecules, with all the endless different types of protein providing something that's fundamentally important to how we work. Take them away, and we simply wouldn't be here. We can go one rung deeper than proteins, however, in the search for life's first building blocks, to amino acids. All proteins are made up of amino acids, which are simpler organic compounds. As such, it's held that life cannot emerge unless amino acids are present at the very beginning, present and ready to form proteins, which then can combine into and power cells, which can then continually join together into increasingly sophisticated multicellular organisms. For some years now, and despite many abiogenesis lines leading to those hot vents at the bottom of the ocean, we've also known that crucial amino acids can be found in space. In general, this is perhaps to be expected. The very first basic elements form in stars, hydrogen and helium, before fusing into other elements, like, again, carbon, nitrogen, etc. We know that our sun and the solar system first formed out of the massive collapse of a once vast molecular cloud. So there was always the likelihood that amino acids would form here from a time before even the sun itself had taken shape. But there are still some patterns at play that have traditionally been difficult to explain, although those difficulties could now be lifted. In April 2023, fresh research was published by a team working at the Pheasant Memorial Laboratory at Okayama University in Japan. The work centers on the question, how were amino acids formed before the origin of life on Earth? And it focuses on the near-Earth Apollo asteroid known as Ryugu. On June 27, 2018, JAXA, the Japanese Aerospace Exploration Agency, successfully landed on Ryugu with its Hayabusa 2 spacecraft, which then spent more than a year navigating the rock before leaving on November 12, 2019. As part of the mission, which is still ongoing, samples from Ryugu were ferried back to Earth, arriving on December 5, 2020, and it's these samples that the team at Okayama University have worked from to establish the origins of amino acids. To set the scene, the study's authors explain that most amino acids come in two forms that are seeming mirror images of one another, similar to human hands, with these forms then often referred to as right-handed or left-handed optical isomers. It further explains that one interesting characteristic of life on Earth is that it uses the left-hand type to form its proteins. In some ways, this means that when searching for the origins of life anywhere, scientists have already narrowed it down by half. With this in mind, the team analyzed two distinct particles from Dugu. Amino acids in general were clearly present in both, leading more weight to the broad idea that life's building blocks do come from space. However, it was also found that there were differences between both particles which could yet explain how, when, and why certain amino acids form. Most notably, one particle was found to have much higher levels of the amino acid dimethylglycine, or DMG. Further chemical analysis then tracks the DMG back to that particular particle at one time experiencing an abundance of water in its ancient past. When the earliest ices melted in the young planetesimals and shards of rock in the solar system, it resulted in the formation of a wider range of minerals, a vital stage known as aqueous alteration. Seemingly though, DMG was much more likely to show up as a result of this as well. We certainly know that liquid water was carried inside some asteroids that had originally formed further out from the Sun, in the early days of the solar system before the likes of Earth and Mars had evolved enough to host water themselves. We also, of course, know that various asteroids have impacted with Earth over the course of its history. It's long been suggested that these monumental events could have brought with them the origins of life. But this study provides a very specific example of that in action, tracing the formation of DMG all the way back to its cosmic roots, but showing that water was still seemingly the key ingredient. Above all else though, this study perhaps serves to highlight the incredible balance and run of existential fortune that's required to make life possible. The catch-all term of life's building blocks can make it feel as though what's needed for life isn't that difficult to get a hold of. But this study shows that those blocks can be literally billions of years in the making before they're suitable for inclusion within any kind of cellular beings. For just DMG, everything has to be just right. The materials, the timing, the chance events, and so on. The team at Okayama University draw on this realization further, writing that the findings of the study indicate that slight differences during aqueous alteration can have big effects on the end abundances of amino acids, concluding that, as some amino acids are destroyed while others are created, this in turn will affect the availability of amino acids at the origin of life on Earth. Finally, another takeaway here is that fundamentally, we really are all a part of the universe, living out our daily lives in our towns, cities, and homes on the ground with the unending sky above us. There's a good reason to be philosophical about the meaning of life, about where we come from and where we're going to. But in a practical sense, we do know why we're here. While studies do differ, those hydrothermal vents in the ocean appear a very strong candidate for hosting the chemical equations that make us here on Earth specifically. But Earth didn't always exist, and in the time before, the solar system was swimming with infant worlds of rock and ice. Even then though, the very first parts of biology were being brewed. Those infant worlds were packed with the potential for something much more complex. It would just take countless, intricate, natural processes, unlikely collisions, and plain lucky breaks plus multi-billions of years to allow it to happen. But nevertheless, that's why today, scientists have discovered and are still discovering the true origin